Alright, 10.3 arcs and chords. Buckingham students will recognize and use relationships among arcs and chords and diameters. Alright, so theorem 10.2. In a circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, so if this chord and this chord are congruent, then we know that these arcs are congruent. And vice versa, if we know that these chords are these arcs are congruent, then that tells us that these chords are congruent. Remember, arcs are the curvy thing, chords are the straight thing. So let's prove this. We're going to actually prove this theorem right now. Alright, let's give myself some maximum space here. It says, use the circle O, this circle right here at the right, given that DB and AC are congruent. So we have this arc DB is congruent to this arc AC, and that is what we're going to start off with, is that DB is congruent to arc AC. And that is the given. And remember, we're trying to prove that these actual chords are congruent, that will lead us to making these chords congruent. Okay, well, if the chords are congruent, we learned a long time ago or not a long time ago, but a couple lessons ago, that means that these central angles are congruent. So we could say then that angle DOB is congruent to angle AOC. And that's because if chords are congruent, then central angles are congruent. Okay, so we can mark that in our drawings. We could say, hey, these two angles are congruent because these chords were congruent, or these arcs are congruent. I keep saying chords instead of arcs, I'm sorry. But the angles are congruent because the arcs are congruent. So these two things are congruent because these two things are congruent. Okay, well, what else do we know is true about a circle here? Well, it looks to me like, hey, this is a radius, and 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 therefore all of my radii are congruent. So I can write that. I could say DO is congruent to OB because they're both radiuses, right? Well, and so is OC, and so is OA. And because they're all radii of the same circle, so we could just say radii of same circle are congruent. That's my shorthand for radii of a same circle are congruent. All right, now take a look at this. Well, it looks like I have a triangle here, DOB, and I have a triangle here, AOC, and DOB has side angle side, and AOC has side angle side. So I'm going to say triangle DOB is congruent to triangle AOC by SAS. Alright, now remember, after I prove triangles congruent, after I can say that all of their parts are congruent, and DB is a part of triangle AC. I'm sorry, DP is a part of triangle DOB, and AC is a part of triangle AOC. Therefore, I could say those two parts are congruent by CPCTC. And there we go. We have proven something congruent. What I want to point out is SAS and CPCTC, this is something we learned in Chapter 4. We're in Chapter 10, and we're still using stuff from Chapter 4, so we can't just ignore it. It's important stuff. We're going to keep using it. Okay. Alright, this next theorem, I did a little activity in class, kind of neat. We used some patty paper, but basically it says this: in a circle, if a diameter or a radius is, I'm going to use the perpendicular symbol, is perpendicular to a chord, then it must bisect the chord and its arc. So I'm going to zoom into this picture so we can add some drawings here. Here we have a radius. And if this radius is perpendicular to this chord, and this chord being AC, that means a couple of things. That means we bisect this chord. So AB is congruent to BC, and this chord AD is congruent to this chord CD. We bisect the chord or gosh, I keep saying the wrong thing. We bisect the chord, which is the straight line, and we bisect the arc. We bisect the arc as well. So AD is congruent to CD. The arcs are congruent. Sorry about that. So that gives us quite a bit of information. Now, what if, in this example here, they give us some stuff. So what if the radius is 13 inches? So let's just write that. R equals 13. And OD is perpendicular to AC, which we marked. OD, perpendicular to AC. And AC, which is 24 inches long. So we could say that AC equals 24. Can we figure out what the arc CD is if the arc CA is 134? And can we figure out, and this is a typo, this shouldn't say OX, this should say OB. Can we figure out OB? Let me just write it again so it looks a little bit better. Okay, well I think that you guys could do the first one on your own. So why don't you guys maybe pause the video and see if you can figure out arc CD on your own. And I'll put the answer up there in just a second. Okay, well, if the total arc here is 134, then CD should be half of that because we bisected that arc. So we just need to take 134 and divide it by 2. That's what arc CD must equal, which is 67. That's it. So that one's easy. Now OB is a little bit trickier. We're going to have to know a couple things. One thing that we need to know is if AC is 24, we should be able to figure out what BC is and what AB is, right? We could figure out that BC and AB must both be 12. So let's zoom into our picture and add that information. So we know that this is 12 and this is 12. All right, well, what else do we know? Well, remember they said the radius is 13. Okay, well, where do I see a radius here? It's not really one drawn. I mean, I guess this is a radius and this is a radius, but how does that help us? Well, this is the trick to these kind of problems. You're going to have to add the radius yourself. And look, from O to C, that would be a radius because it's going from the center to a point on the circle. So let's just draw a little line here. And that is a radius, so it must have a length of 13. And now you're going to be able to see that this is a right triangle with an unknown leg, a leg of 12, and a hypotenuse of 13. And hopefully you already have these numbers memorized, but this is a Pythagorean triple. We have a number here, 12 and 13, and I'll show you how we can find that in case you forget the triple. We can always just do let's call it x for now. We can always do x squared plus 12 squared equals 13 squared. X squared plus 12 squared is 144, and 13 squared is 169. So let's subtract 144 from both sides. And 9 minus 4 is 5, 6 minus 4 is 2, and 1 minus 1 is just 0. So we get x squared equals 25, and then we take the square root of both sides, and we get that x equals 5, because I square root. So x equals 5. So this is a length of 5. So what I wanted you guys to see is that this is a 5, 12, 13 triple. And that's one of the ones I told you to memorize. So if you had that memorized, you didn't have to do all that work. You just know, oh, it's 5, 12, 13, bam, I'm done. So OB must be 5. All right, let's go to the next page. Okay, just a couple things here. In a circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so we have a chord AC and a chord FD here, and yeah, sure enough, they're both 10 from the center, so they're equidistant from the center. So we know right away, we could go over here and we could say, hey, we know that AC is congruent to FD. And we also know, we also know that if we're finding the distance from a line to a point, it has to be at a right angle. So we know that these are right angles. So I'm going to zoom in and mark that. I'm going to mark that this is a right angle and that this is a right angle. Okay, and then they say chords AC and DEF are equidistant from the center. If the radius of circle G is 26, find AC and DE. Okay, we need to put in that 26 for the radius. So let's zoom in. Well, where do I have a radius here? I have a radius here, and I have a radius here. So let's go ahead and just put that in. This is 26, and this is 26. Alright, once again, I'm hoping that you can see how we could find this, because if this is a right angle, it must bisect this chord. We learned that, right? Because this is part of a radius here that is perpendicular to a chord. Therefore, it bisects the chord. So let's mark this and this congruent, and then this and this are congruent as well. So we have 4 things here that are all the same. And what I'm hoping that you see is we have a little right triangle with a side of 10, an unknown side, and a hypotenuse of 26. I'm hoping by now, if I was to call this x, you could see what x must be. Instead of 5, 12, 13, everything's doubled. So it's going to be 10, 24, 26. Same thing here, 10, 24, 26. So before we had the triple 5, 12, 13. And the same triple works if you just double it. So 10, 24, 26. That's a triple as well. And so 24 is the missing part here. So that means this is 24, this is 24, this is 24, this is 24. Alright, well, what do they want us to find? They wanted us to find AC and DE. Well, AC is this total distance, so it'd be 24 plus 24, so that's just 48. And DE is just this little distance, half of 48, or just 24. So there we go. AC and DE, we found them. Easy enough. Alright, for the summary, I want you guys to be able to use the picture above and tell me if arc AC is 120 degrees. Describe how you could find the measure of arc FD. How could you find this arc measure? Be sure to explain your reasoning using theorems you have learned. So all you know is that they're equidistant, that these chords are equidistant from the center, and then you have arc FD and chord FD, arc AC and chord AC. And I want you to just explain to me how you know it. And hopefully you can tell just by looking at it that they are congruent. And hopefully you can just see that, but I want you to be able to explain to me why. So you already know that AC and FD are the same. So you already know that FD is 120 degrees. But what I want to know is why. Okay, that's the kind of logic we need to be able to do in geometry. So spend some time thinking about it. Make sure you can answer it. Basically, you're going to have to use 2 theorems to prove it. So go for it, and see you guys in the next video.